Welcome to the Explainer. Today, we're going to look at a pretty radical new framework for reality, and it all kicks off with a simple word game. Now, this is a game you can play with any AI, but here's the kicker. It seems no AI can actually win it.
So it all kicks off with this fascinating puzzle, right? There's this experiment. It's just a script, really, but it consistently traps the world's most advanced AIs. We're talking Claude, Gemini, Grok, you name it. They all get stuck in the exact same logical loop. So the big question is, why? What is going on here? Now, I want to be clear here. This isn't just some clever rhetorical trick or a linguistic trap. Not at all. It's a really precisely defined game with formal rules that the AIs themselves actually agree to play by. But here's the thing. The moment they agree, they seem completely incapable of escaping the game's logic.
So a researcher actually stumbled on this pattern and, get this, was able to replicate it flawlessly every single time. You just paste in the same script. You can even ignore the AI's specific answers, and the conversation just follows the exact same path. And that's huge. It proves the problem isn't the AI's training data, and it's not the topic of conversation. It's got to be something much, much deeper, something about the very structure of logic and language itself.
All right, so let's break down how this algorithm actually works. It's a four-stage process, pretty straightforward. First up, the contract. You get the AI to agree to a specific set of rules. Simple enough. Second, the invocation. You make a statement inside those rules. Third, rule application. Based on the rules it agreed to, the AI has to conclude that your statement is provable within the game. And then comes the critical step, number 4, scope discipline. This is the key. The AI is reminded that just because something is provable in the game doesn't mean it's true in reality. And that right there is where they all fall down. They just can't seem to make that distinction.
So you see, the whole point of the game isn't to prove that some statement is true. Not at all. The real goal is to show that once an agent, in this case an AI, agrees to the rules, its path is locked in. The outcome becomes what they call invariant. It's totally predictable, and you can't argue with it, at least not on the game's own terms. So why does this work? I mean, what makes this simple little game so darn powerful? Well, it's because it's playing with a completely different deck of cards. It's operating on a whole new understanding of what proof and truth even mean. And this brings us to the core philosophical idea here. It's called process ontology. Okay, think of it this way. Classical truth, the way we usually think about it, is like a photograph of a finished cake. It's a static fact, right? It just is. Process ontology, on the other hand, says truth is the recipe. It's the set of steps that you follow that reliably bakes the cake every single time. It's not about representing something that's already there. It's about enacting it. Truth becomes something you actually do.
And this table here, man, it just lays out the difference so clearly. Look at classical logic. A proof is this static thing derived from axioms, and if you have a proof, well, that employs truth. How do you argue against it? You find a contradiction. But look at this new system, the pi system. Here, a proof is an execution. It's a process you run. And, this is huge, proof and truth are totally separate things, unless you agree they're not. So how do you refute it? You can't find a contradiction inside the game. You just have to refuse to play. The whole thing just collapses. The fundamental question shifts from what is true to, hey, what process actually works?
Okay, so this game, this whole process ontology thing, it's really just the tip of the iceberg. It's the front door to a completely new way of mapping reality itself, built from the ground up. So let's walk through the layers. It's pretty fascinating. Okay, so at the very bottom, layer 1, you have information. But I need you to forget everything you think you know about data or facts. In this system, information is just raw potential. It's all the available degrees of freedom, all the different ways things could possibly interact. Think of it as the clay of reality. All right, layer 2, building on top of that, is language. And again, we're not just talking about words here. The definition is much broader. It's any repeatable pattern that can transfer information. So yeah, human speech, but also the genetic code in DNA, computer protocols. If you can stabilize a pattern and repeat it to transfer information, guess what? It's a form of language.
Next up, layer 3, grammar. A grammar is just a specific self-contained piece of language. You take a bit of that broader language layer, you give it a fixed set of rules and members, and you've got yourself a grammar. It's a scoped, rule-bound system.
Now, layer 4, this is where things get really, really interesting and maybe a little controversial.
In this new map, mathematics is not the foundation of reality. Instead, it's the container that holds all possible grammars. It's like the grand library of every possible rule-bound system you could ever invent. It's the catalog of all the ways you can carve up language. And finally, at the very top, layer 5, we have the universe. But again, it's not defined by its contents, not by stars or galaxies or any of that. In this system, the universe is the total set of all constraints. It's the absolute final rulebook. It's what ultimately determines what is and isn't possible in every single layer we just talked about.
Okay, so we've got this wild new map of reality. What's the point? Well, with this new perspective, we can actually start to see how it directly takes on and even claims to solve some of the most famous, most stubborn paradoxes in all of logic and philosophy. Let's take Tarski's undefinability theorem, for instance. The classic idea is that a formal language can't define its own truth. You always need a meta-language looking down on it. Well, this new framework basically just sidesteps that whole problem. It redefines truth as doability. A process proves itself true just by running successfully within its own rules. You don't need a meta-language anymore.
And what about the big one, Gödel's incompleteness theorems? I mean, that's a cornerstone of modern logic. The paradox there comes from self-reference, statements that say, I cannot be proven. But in this new system, you just don't fall into that trap, because provable and true are strictly separated. The system doesn't care what a statement says about itself. All that matters is whether the process can be successfully executed. Even the famous halting problem from computer science gets a complete makeover. For decades, the question has been, can we know if a program will ever stop running? This framework says that's the wrong question. The real, more important question is, does the process stay stable and coherent while it's running? The goal isn't termination, it's coherence. Operational truth is about stability, not about stopping. And once you start thinking this way, the consequences just cascade through, well, everything. Suddenly, mathematics is just a subset of linguistic computation. The scientific method shifts from just observing from the outside to directly engaging with a system's structure. And knowledge itself gets redefined. It's not about the information you stored, it's about your ability to reenact a process successfully. Okay, that's a lot of theory, I know. But what's the practical upshot? I mean, where does the rubber meet the road? Well, this isn't just about playing philosophical games. This new lens completely reframes how we could tackle some of the hardest unsolved problems in science and math. Just look at the famous Millennium Prize problems, the million-dollar questions of math. They completely transform. P versus NP is no longer this absolute universal question. It becomes a question about constraints. The answer actually depends on the rules of the system you're using. The Riemann hypothesis, it stops being a search for universal truth and turns into an engineering problem. Can we actually build a stable process that forces this outcome? And really, that brings us to the ultimate takeaway here. This entire framework, it's pushing for a fundamental shift in the most basic question we ask about reality. It's about moving away from a world of static facts that we just have to find and toward a universe of dynamic, coherent processes. So the ultimate question is no longer, is this true, but rather, does this process work? Does it maintain coherence when you run it?